record. I assume you guys can see my screen. I always have this Coach Jay Johnson workout that I do open. I should just like favorite that thing. Let's see here. Okay, so just a reminder real quick. We are, no, I don't want to do this. All right, anyway, well, I don't want to do this because you guys can see my password when I type it in. So we will, it won't just autofill it. Okay, so anyway, so we have an exam next class. After this class is over, if any of y'all have any questions you want to work on, we can kind of talk about these things, et cetera, et cetera. I did kind of, give me 1 second. We're gonna share a whiteboard here. Let me see my phone here. I think I'm on Moodle here. Okay, oh, where's my whiteboard? Come on, you can do it. Okay, give me 1 second. Moodle. So I'm a little discombobulated from sitting there doing nothing for 1:15. It was a very good test, although it was a little hard, or a little long. I don't think it was hard. Maybe like, 3 or 4 minutes too long. Let's see here. Okay, so you guys can't see what I'm doing on my phone, which is unfortunate because I was going to kind of show you where we were and whatnot. But anyway, so there's an exam next class. It will be in the Doze auditorium, whatever they call that fancy auditorium. And I think that's all we need. Are there any questions about the logistics of the exam?
Where is that at? How do you spell that, by the way?
DOHSE.
That's
so
just the engineering auditorium.
Yeah, it's like okay.
Across
the breezeway from the rest of the engineering building.
Okay.
So like, I mean, I think technically it's in the engineering building. It's called Engineering Room 101, Engineering EN 101. But yeah, it's that big auditorium that if you ever seen any kind of presentation or something, they always go on in there. If you haven't, then you probably haven't been in there. Or maybe they've done like club meetings over there or something. I don't really know. Anyway, yeah, so when you're in there, I'm going to give you a copy of this. Basically, I don't know if you guys can't see my screen, but anyway, or you can't see what I'm holding up, I don't think, but it's just the fluid mechanics FE equations. It's really quite long. Fluid mechanics has a lot of pages, whereas the other classes are not so long. Like my statics class was like 2 pages, and for you guys it's going to be like 8 pages of equations. So I do recommend that you've been working with those equations so that the sheet doesn't confuse you. Yeah, any other questions about it? Okay, so yeah, so I recommend
one question.
Sure.
You had said earlier that studying the old test would be one of the best things you can do.
Yep.
Okay, perfect. Just want to triple check. Awesome. Thank you.
Yeah. So the plan then, so that is one of the best things. If you're like weak on something, if you're like, I'm really struggling with manometers or something, then what I would recommend is going into old homework. So I don't remember what I called the tab on Moodle, but there's one called old homework or something like that. And you can just scroll down and look at the topic that you want to do some problems on. And old homework, maybe you can find 10 different manometers that you could like just work, and the key is there too, so you can solve those. Obviously some of those are a little messed up because the key isn't perfect. Like maybe I gave the problem and I forgot to give a value or something, so I solve it without the value, or I don't know. So but over the years there's enough problems in there that you should be able to work them. I am going to add a little variety to them. Like if you go look at the old tests, actually I only have 2 of them up right now, or 3 of them. I'll try to get more of the old tests up, but I am going to add some variety. If you look at them, they almost all have the same topic of problem. So I'm going to probably switch them around a little bit so that it's not always the same topic. So otherwise I have all my students studying these 4 topics and I do these 4 problems and ignoring everything else. and that's no good. So you'll have 10 true false, followed by two or three like short calculation problems, like basically, one equation solvers. And then after that, you'll have three that are a little bit more involved, like force on a gate, for example. For the force on the gate one, basically, I'm going to pull out a dice. And if you look at the old exams, you will see that there has never been one where I've given a class a force on a gate on a curved surface. That can always happen. I roll the dice. There's a 1 in 6 chance any semester. I've taught it. This is my 7th semester teaching it. So, whatever the roll is, I'll decide before I roll it, a 1 or I'll say like a 1. And if I don't roll a 1, well, then you don't get the curve problem. Okay. So it's up to you. You can decide, I don't want to worry about the curved one. Maybe that works out for you. Maybe it doesn't. Okay. So, anyway, any other questions? Okay. After this is over, after we finish this, if anybody wants to hang out and ask me any concept questions, we can work whatever it is you want. Okay, so here we are, flow regimes and flow rates. And okay, so here's the objectives. Oh, somebody from California is calling me. That means they want to sell me my some car stuff. Okay, objective 1, we're going to classify flow regimes. Does anybody know what a flow regime is? Okay.
Sounds like a political party.
Sounds like what?
Sounds like a political party or something.
Or like a hip hop group.
Oh, flow regime.
That would be.
I think I like that. My band will be Flow Regime Thud. I've been thinking that when I come up with a band, I want it to have the name Thud in it. Flow characteristics and the Reynolds number. Okay, so basically what we're getting into is laminar versus turbulent flow. And then another objective is we're going to classify the dimensionality of flows. Okay, so this one right here, this first one, really important. The dimensionality of the flow is just kind of a way for you to think about a flow that can help you kind of like simplify it in your mind. And so basically this is it 1D, 1 dimension, 2 dimension, or 3 dimensional flows? And then the last thing, and this is really important throughout this class, is the compute what we call the volumetric flow rate and the mass flow rate. Basically, if ever they ask you what's the flow rate, they usually mean volume. I guess if you were doing air or something, you might be more interested in the mass flow rate. I don't know. I never play with gases. So at some point, we'll go into we'll work with some of these videos here. I can't believe I forgot my computer at home. Anyway, so here we go. So well, let's just kind of put this here, and I'm going to do laminar versus turbulent flows. Okay. Does anybody have any idea what laminar versus turbulent flow means? I mean, you could probably think like, what does turbulent mean to you?
Laminar or smooth.
Yes, smooth. Like that's kind of the main thing that we like to think of with laminar. It's also predictable. Okay. Now, turbulent, on the other hand, I don't know, what's the opposite of smooth? Like rough? You can call it rough. Typically, we would say it's irregular. And instead of predictable, we would call it chaotic. Turbulence is one of the great unsolved mysteries of science. Just trying to mathematically describe turbulence is something. I mean, there's whole fields on this. This is just an intro to fluid mechanics, but if you wanted to go into turbulence as a field, there's a lot out there. Okay, so this is laminar. Laminar is governed by, the shear stress equals the viscosity times d, whatever, d, some velocity, u, d, some direction. We'll just call it dy for now. Okay, so whereas this mu right here, this is molecular. I really wish I could see my computer right now. All right, so so over here in the turbulence thing, there's more shear stress, okay, due to more exchange. Okay, so if we go back to, way back in the day, okay, when I was talking about, what is viscosity, what is it, how, where does it come from, et cetera, et cetera. And so I was like, okay, well, imagine you've got, fluid or whatever, and it's flowing between two walls. And so let's imagine we've got a layer of fluid. So here we've got some kind of velocity profile. Let's imagine it's parabolic, more or less. Okay, and I think about one little layer right here. Okay, and I think about the layer next to it. All right, so the layer next to it maybe is not quite going as fast. Okay, so the way we think, we've always been able to think about this in two ways, or two reasons. One is molecular attraction, the things that cause viscosity. One is molecular attraction. All right, so we've got a molecule here, and we've got a molecule here, and because they like each other, the slower molecule is pulled to speed up, okay? And the slower molecule is pulling on the faster one to slow it down, okay? And that causes an exchange of momentum between the two, right? So like if you're running along and you're running with your buddy and your buddy's not as fast as you, your buddy's gonna pull you faster and you're gonna pull them slower, okay? So that's gonna cause a stress between, on your hands, right? So that's one possibility. The other possibility is that, so this is the things that cause viscosity. The other thing is there's exchange, okay, which basically means there's a molecule in this, row, and there's one in this row, and just due to molecular action and whatever, not so. This one is going to go, so this molecule is going to bump up there. This molecule will bounce down there, just because molecules move kind of irregularly, and so when they do that, we end up with, basically some of the high momentum fluid moves into the low momentum column, or not column, but row. And some of the low momentum fluid moves into the high momentum column. And so it has the tendency to slow down the fast layer and speed up the slow layer. Okay. So both of those things occur in this viscosity term over here. So however, over here, there's more stress due to more exchange. So basically, come here. Can you just underline something for me? Thank you. So over here, what happens is, as things get turbulent, okay, as the flow gets more irregular, instead of molecules just exchanging, say, this far apart, okay, due to like molecular exchange, there's more exchange due to like kind of like macroscopic. So like instead you might see eddies and swirls and things like that are happening in this fluid. And you can imagine that these swirls are much, much larger. And so instead of the exchange just happening between two layers that are really, really close to each other, we might have, like in this case, we might have an eddy that's this big. I don't know, I'll give it a name, lambda. We're not going to get into lambda, but there is an eddy. There's a size limit to these eddies. But these eddies will kind of, you'll have more exchange over larger length scales, because this is, instead of it just being, between these two little layers, it can, there's you can get these big, beautiful, I mean, they're really kind of beautiful to watch, eddies. So, so over here, we would say the molecular viscosity dominates. Okay, that's this guy right here, dominates. Okay, and these are kind of the two key points here that I want to drive home, is that laminar flow is unstable as the velocity increases or the viscosity decreases. Okay, so basically, as the flow gets faster and faster and faster and faster, eventually, well, yeah, here I'll kind of draw this out as best I can. So let's suppose we have, a flow, and it's kind of like cruising along, and it's not going real fast, right? So it's laminar, it's nice and clean, blah, blah, blah. And then it's going faster and faster. Okay, and all of a sudden you get to some point where you're going fast enough and you have one little, and basically the way I look at it is you're going fast enough where if there's a perturbation in the flow. So like, let's imagine there's the tiniest, like almost like microscopic bump on the bottom or the top of this thing somewhere, right? So then what will happen is as the flow comes to that little microscopic bump, like, and you have them obviously, like nothing is perfectly smooth, right? It's close, right? And of course the fluid is made of molecules, so they're not completely smooth either. So you don't even really need something to trip it. But I always think about it as if you've got something over here that's going to trip it. And what happens is all of a sudden you're going fast enough where when that thing hits that bump, right, the flow goes, it has enough momentum to kind of like leave that wall. And as it does, instead of like, over here where there was a little bump and it just kind of like smoothly went around the bump and went back down to where it came, this time it had enough momentum to kind of head into the flow. And as it does that, it affects all the other molecules around it, right? So it's bumping into all these other crazy molecules, and you might end up with like a little swirl like this, which of course then affects another swirl this way, and et cetera, et cetera. And pretty soon you get, a very chaotic, system. And it's not something that we can accurately predict. I mean, we can predict the statistics of it, but we can't predict a specific, like we can't just, I can't say like, okay, I'm going to put a sensor right here and I know what the velocity at that point will be at a given time. Okay. So there might be all these crazy eddies doing all these interesting things downstream of wherever this thing was tripped. Right. And so they're, doing all the things that they're doing. However, if you were to take a snapshot, not a snapshot, but a slightly longer term average of it, it still looks like this, right? It still might look more or less parabolic. Okay. This might be the long-term, the long-term average. Okay. And this actually, I'll say this real quick. For laminar, this is parabolic. Like it's actually pretty, you can actually, the nice thing about laminar is we know the equations that describe it. You can actually, well, as long as you're in a large enough scale environment, you can actually kind of solve for simple cases like this, and you can solve and show that it's parabolic. However, in the turbulent case, okay, this is more uniform. And the reason for that is, so when I say it's more uniform, let me draw this red a little bit cleaner. It's more like this, like it's almost uniform across the middle. And then there's like a high stress region near the wall. Okay. So like there's a flat front to this, I guess, would kind of be the way to describe it. And you might wonder why that is. And I hope you're wondering why that is. And the reason for that is because, there's more stress due to more exchange. And then that means that the greater exchange, okay, creates a more uniform profile, creates a more uniform profile. Oh, profile. Okay, so basically, if I look over here at, let's say I look at this one right here, let's use like blue or something. Okay. If this particular particle can move all the way up here because that's the size of the eddies, and this particular particle can move all the way over there, okay, and the same thing can happen here down to there and here over to there and, and everywhere else in between, then what this thing is doing is it's taking all that high momentum flow from the middle and it's moving it out towards the edges. And it's taking that low momentum fluid from the edges and it's moving it in towards the middle. And so you could think about it as mixing. In fact, that's exactly how we think about this. And so this whole middle area is mixing. And so the momentum is mixing such that it becomes, well, mixed, so that, you know, it all basically has the same momentum. So on average, it's all moving at the same velocity. On the walls, we can't quite get there because on the walls, right, there's a no slip condition. So there's all this friction on the wall, which is holding the fluid back. And so there will always be these kind of like areas on the edges where there's just, you know, this would be the high stress regions of the flow. High stress because the du, dy, or du, dz, or, you know, whatever coordinate you're thinking about. But there's a velocity profile on those edges, and that's where the stress is. Okay. Any questions on this?
Related to the viscosity thing, I was curious. When you're looking at higher viscosity and lower viscosity, what are we looking at in terms of the molecules being either repelling each other or close together when you're looking at a higher or lower viscosity? How are they behaving?
Well, okay, so higher viscosity would be, so I always think of honey and water.
Yeah.
Honey has a higher viscosity than water. And I don't really know why, but for whatever reason, the honey molecules attract each other more than the water molecules, right? So we've got higher molecular attraction between the molecules of honey than we do through water. And I would imagine we have less exchange. Now, of course, in this case, like a lot of cases, you know, with honey, you know, that changes very rapidly if you heat it up, right? If you heat it up, you lower the viscosity of honey because you can pour honey if you nuke it, or if you know, boil it, or whatever it is that however it is you make your honey, you know, usable. You know, so like, but, you know, to that end, you know, unstable is, you know, if you had just your regular honey, that's like almost like crystallized, it's going to be awfully hard to get a turbulent flow in honey, right? You're going to have a hard time getting the velocity to go up or getting the viscosity to go down. Okay. The only way that you can really do that is if you really nuke it. So the viscosity goes way down. And then even then, I have a hard time imagining that you can, you'd be able to, you know, to get it to go all the way down.
Right.
So hold on, I'm gonna, any other questions on this? I want to show you all some demos real quick. Let's see here, clear all drawings. Let's stop this share. Come here, punk. Let's see, share screen. Start broadcast. Yeah, I know. Come on, you can do it. All right, let's see here. Give me some YouTube. Where are you at? Okay, here's some YouTube. Give me some. What are we looking for? We are looking for, laminar.
I got Jeff Hansen in my search history too.
Laminar dye experiment. Yes, I teach statics, and so here we go. This is really, really, really cool. I highly recommend this guy, Smarter Every Day. He's pretty cool.
He's amazing.
He gets really excited about laminar flow. I want to show you something. This is the reversibility. So this is a 2-minute video. So I'll kind of talk you through this, but this is a laminar flow. And so, you know, all those chaotic motions I was telling you about? The thing about those chaotic motions is that they're irreversible. Like you can't, you know, but in a laminar flow, things are reversible. So this is the most interesting 2-minute video in the universe. So this particular, they're probably putting this dye into some glycerin.
I can't see the
Screen is frozen.
What? Speak up.
Now
It was frozen for me.
Is it still frozen?
Now I just see the 2 dots, but it's not moving.
I mean, it's slow. Can you see them putting in the 3rd dot?
No, it might be my connection though.
Anybody else?
No, I'm not seeing any movement either.
Okay.
I'm not seeing it either.
School
Okay.
Wi-Fi.
All right. let's try sharing screen again.
It
No,
showed
not
up
that.
after a
Oh,
second and it just had a real bad lag.
okay. Well, maybe this will just be like, let's see, maybe this will be like homework, watch this video. I mean, this video is really cool. Let's see here, share content. Come on, screen. Start broadcast. Okay, let's see if we can do this. Let me skip trial. All right.
All right, now we're going to
Can y'all see it now?
these fairly
Yes.
slowly.
Okay, so basically they've got a really viscous fluid. So this is probably glycerin. So it's just like, think of it as like, really sticky honey, except clear. And they put 3 dots of dye in there. One's red, one's green, and one's, I don't know, purple, indigo probably. Aren't those the primary colors? I don't know. Anyway, so they put them in there, and this is like that viscometer we did in homework.
All right, now we're going to
problem one.
rotate these
And so they're
fairly
rotating the interior
slowly
while the outside wall is staying where it
5
is.
times.
And you can see they're going really slow. So this is a laminar flow because it's really viscous and it's really slow moving.
Notice the flow is laminar because the Reynolds number is less than.
Okay, and they're talking about how the Reynolds number is really low. They've done a calculation. We'll talk about the Reynolds number in a second.
This is 3.
But as you can see, it just keeps going around. And of course, that's shearing those dye, right? The dye on the inside is moving faster than the dye on the outside.
5.
So even within each of
Now
those
we're gonna go
blobs, the
back.
inside is now gone further around than the stuff on the outside.
Backwards,
So now they're going backwards.
backwards 2. Backwards 3. Backwards 4. Backwards.
You need to go half a rev. Keep going.
Oh, I see.
Go one more. One more.
It's a good thing we have a couple of coaches here. Very good.
And there you go. Completely reversible behavior. Okay. And it's because the fluid.
There's no more room in hell.
I don't know about when there's no
The
more
dead
room in hell.
walk here.
I don't understand how people watch this stuff. Anyway, so hopefully, let's see, stop share. Hopefully you guys appreciated that. I think that's like one of the coolest experiments I've ever seen. And what it's showing to you is about the reversibility of the flow. And so basically, like, the flow went forward and then the flow came back. And we don't think of that as possible, usually because things mix out. But the reason that things mix out is because of irregular, either molecular diffusion, but a molecular diffusion is very slow, or due to turbulence. Okay, so that would be, we actually call that turbulent diffusion, but it's why, like, I don't know if you've ever tried this. If you guys drink coffee, put some cream in your coffee and don't stir it, and see how long it takes for the cream to just kind of like mix out into the coffee on its own. Okay, you really don't want to do that. It's going to take a day or something. I think my fluids professor told us it would take a day and a half. I mean, he's obviously guessing based on the math. I've never actually done the math. It wouldn't actually be all that hard to do. But of course, if you give it a quick stir, it goes much quicker. Okay, so all of the irregular motions are irreversible. All of the the regular, controlled, whatever, those are completely reversible, and that's what they just demonstrated. So hopefully, maybe I'll give you. Let me do one more video here. Let me see what we can do here.
Is that first video on the link section for all the other videos?
Yeah, I have all the videos on whatever on the Moodle.
Okay.
If I could get into Moodle without showing y'all my my password, I would. That would actually be fun. I would love to see what you guys would do if you got into my Moodle. Okay, let's see here. Start broadcast. Come on, punk. Okay, here we go. Let's see what we got. Let's see if we can get some YouTube here. Come on. Thank you. Okay, let's do laminar versus turbulence. The nice thing about these are pretty easy, easy to find, and I have a few of these on here. Let's see. I know exactly. Yeah. So this guy right here, this guy gets really excited about laminar flow, smarter every day. His enthusiasm is what makes it. It's what makes watching him worthwhile. Here you go. So this is a good example, especially because I don't think they talk in this one. But you can look at these two different flows, and you look at the one on the left, and you can follow a dot, and for the most part, they're just going up. You know, like I can't really draw on it, but it's what we call a kind of a pretty smooth flow. I mean, there's a little bit of exchange. I would say it's not 100% laminar. The one on the right, the flow is a lot faster, but also they put that wire around the outside, and so that kind of trips some turbulence. So you can see, like, just downstream of those wires, you know, that wire, you can see the particles just going kind of crazy, and they're going all over the place. And so this is kind of the difference between laminar versus turbulence. And of course, most of the time, almost all of the time, we're dealing with turbulent flow. Yeah, when they slow it down, just watch a little dot on the right, or watch one on the left. You see the ones on the left are pretty much just going up, and the ones on the right are going left and right as they go up. You could imagine doing like a time average of the ones on the right, and you know, on average, the profile is not going to look all that different than what we see on the left. But you know, but yeah, but I mean, you know, all that chaotic behavior on the right is not on the left, and so the chaos of that creates a problem for us. And at some point in time, we're going to have to deal with that, and we will later in this class. This will be the first time that we start to kind of deal with things as they actually are. In this class, as opposed to being like, you know, oh, a frictionless pulley, a frictionless thing. Oh, this door has no weight. We're actually going to start to deal with that. And I think that's probably one of the coolest things about this class. So we'll get there. I don't know for what purpose they created this video, but I do like it as a visual. Oh, here we go. This is a great visual too.
Who are you? You
I don't know about you guys, but they
vaguely
love
familiar.
trying to get me to watch Cruella. They also like to try to sell me.
In the last video, we started to look at what happens when water flows through a system being used is not injecting the dye perfectly smoothly, but we can still see that once the dye is
so
in
this
the
is kind of
pipe,
like a laminar
it doesn't
flow.
change
It's not
shape
perfect,
as it moves along the flow.
but you can.
The second
This guy's
characteristic
got a
of
whole
laminar
lesson. We
flow
should just watch
is
this.
that we get a
Here's a
velocity
turbulent
profile. Dye
Look at
is
how
being
much
injected into a
more it
turbulent flow,
mixes.
and we can
Okay,
now see
and
the
it's just
flow
kind of
is
responding to
behaving very
whatever's going
differently.
on.
Turbulent
Thank you,
flow is
turbulent flow.
characterized by
See
chaotic
if we can get these
swirling
side by
eddies.
side.
And these eddies will transport fluid particles in all three.
Yeah. Okay.
So the particles spinning will propagate into full-scale turbulence.
Anyway, let's see if we can
So
get
now
the
we've
two
thought
pipes
about the
side by
theory
side.
and discussed Reynolds number as a
Anyway, so
method
this
to
is,
work.
you know, I should probably actually recommend this. I'll have to watch this video to make sure that the guy doesn't say something silly.
And turbulent flow, where we have
Anyway, so that's the idea behind turbulence and what turbulence is. It's just these chaotic motions that happen in the fluid. So where's my whiteboard? Come on, you can give it to me. Okay, now what we do to characterize when it happens is we use what's called a dimensionless number, and the first one of these we're going to work with is Reynolds number. And depending on what field you go into, like if you stay in fluids, there's so many dimensionless numbers, like they're all over the place. And so what a dimensionless number means is that it has no dimensions. Okay, so it has no units. Now this is important because it means that whatever you plug into solve for it, you must make sure that it ends up with no units. Okay, so the Reynolds number is usually written as RE, so it's named after Ozzie Reynolds, or Oswald, I think as Oswald Reynolds. And it looks like this: the density times the velocity times the length scale divided by the viscosity. Okay, and another way to put that is to combine these two terms right here. Okay, you guys probably don't remember because we haven't used it that much, but those two can be combined such that mu over rho is the kinematic viscosity. Okay. And so it's like when you first start seeing this, it's very hard to imagine what the heck this might mean. And so I'm going to kind of talk about this in a little bit. And this is something they always say, and it always kind of annoyed me because I was like, I don't know what any of this means. Is they said, okay, this is the ratio of the inertial to the viscous forces. Okay, and I'm going to try to explain that in a second. And so basically, there's a transition from laminar to turbulent flow around a certain Reynolds number. Okay, and that Reynolds number is determined empirically. Okay, so this word empirically always bothered me. Empirically, because I had no idea what it means, and that just means that they studied it and they got a number. Okay, and so what that means is, and so this is the weird thing, right? So kind of like, okay, well, you've given us you're saying a velocity and a length scale, but you haven't said what the length is that we care about. The length of what? And the velocity of what? Because like inside of a pipe, so if I imagine I have a pipe here, so let's say here's a pipe. Okay, and yeah, is somebody speaking? Oh, okay. Y'all still there, right?
No.
No, not still here. Okay. All right. So in a pipe, you can imagine, well, there's probably a few different lengths. Like it could be the length of the pipe. It could be the length of a lot of things. You know, like I could say, well, what is this? This is the length of the pipe. Okay, this is the diameter of the pipe. Okay, I could also use the radius as a length if I wanted to. Okay, so those are three perfectly good length scales. Maybe I don't want to call this length capital L because that kind of would tell you right off the bat that, oh, it's going to be the length of the pipe. Okay, and then we might say, well, what about the velocity? Well, you know, there's a few different velocities here, right? So maybe the flow is going through here. Maybe it's going, I don't know if it's going laminar or turbulent, so it might be flat profile like that, or it might be, you know, parabolic like that if it's laminar, I don't know, right? And so what velocity goes in and what length goes in? And so what I'll tell you is that for a pipe, okay, this has been determined empirically. So what that means is somebody already said, you know, for a pipe, the velocity is kind of like this average velocity equals, let's say, u mean. Okay, or really, I guess the way we would typically say that is would be like u bar, so the average velocity. Okay, typically, and then for the length scale, okay, typically what we would do is we'd say, okay, well, what length scale matters? Well, if we're talking about turbulence, okay, the eddies are what we care about. And the eddies are controlled by this. Okay, so it could be either the radius or it could be the diameter, but we use the diameter. And the reason we use the diameter is because whoever did this empirically, they used the diameter. Okay, so what they say in a pipe is that Reynolds number, this for a pipe, Reynolds, so this is all for a pipe. Reynolds number greater than about 2,000, we'll say it's turbulent. Okay. Reynolds number less than about 2,000, we'll say laminar. Okay. And so you might say, well, you know, why D? Well, the reason for D or R, either one, is because if you think about these eddies that might form within the turbulence, okay, they cannot get bigger than the pipe itself. Okay, that's the biggest one that you could possibly imagine. Okay, obviously it can't go bigger than that, or else it would be busting the pipe. Okay, And so you could use R because you could say, well, those things are probably, they probably don't get bigger than, really half of this thing. And that's actually true. I mean, on general, probably the biggest ones are about 40% of the diameter, but it doesn't really matter as long as you're consistent. So basically what somebody did is they did the experiments, whoever did this first, and they did it with diameter and not with the radius. And they did it with the mean velocity. And that's how they worked it. And so they got a transition around here. Now, one thing that's going to pop up in your head is you're going to be like, okay, so if I get a Reynolds number of 2001, it's turbulent. And if I get a Reynolds number of, 1900, it's laminar. The thing is, you're almost never going to be near this number. So if you're near this number, okay, then you're in a transitional region. Okay, and it's like problematic, right? Like it's kind of like, what do we do in that transitional region? It's not really clear or easy. Okay, so sometimes you'll have to make a judgment call. And we're not there yet, but when we get to lift and drag, I'll kind of show you that there's ways that at 2000, you could be either laminar or turbulent, and it kind of depends. So usually, like if the flow were turbulent and you were and it was slowing down, then it would maintain that turbulent characteristic. If the flow were laminar and it was speeding up, it might be beginning to show some characteristics of turbulence, but not full-blown turbulence. So usually what happens is when you calculate your Reynolds number, you go by orders of magnitude. So basically, if it's over 2 times 10 to the third, it's less than 2 times 10 to the third. And usually for most laminar flow, you're going to find like I calculated the Reynolds number, it was 100. And for a turbulent thing, I got like 5 times 10 to the fifth. Usually it's like many orders of magnitude larger than the transition. So usually we're not in the transition. But when we get into lift and drag, we'll talk a little bit more about these transitions. This is the science side of all of this. And I find this very cool. But from an engineering standpoint, we don't usually worry about the science of this too much. For some of you guys who are MEs and things like that, there are some really cool things. Like, I was talking about there could be a little bump or whatever, and that might cause turbulence to start. Like I remember years ago reading about somebody who was a mechanical engineer somewhere, and they were trying to make a engine that combusted better. And so they had I'm not an ME, so I don't do thermo and things like that, but they had something, and the gas came in, the gasoline came in over here, and there was air that came in over here, and they wanted to mix better because, this was a combustion chamber. And so the better it mixed, I guess the better the combustion was or whatever. And what they did is, and it took them all, because they wanted to do this cheaply, like they figured the better this mixes, the more, the air and the gas, the more clean your combustion is. And of course, what they didn't want to do is they didn't want to have to put some kind of mixer in here, because I don't know, that just, it's a waste of energy, or not a waste of energy. So what they did is, in their first experiments, they just took this chamber apart and they just roughed up the top with like a chainsaw or something. And they put it back together, and all of a sudden you got much cleaner mixing in here, because you initiated some turbulence, and boom, it was mixing a lot better. And because it was mixing a lot better with no energy from them except, roughing up the top, they were able to get an engine that functioned a lot smoother. So that's really cool. Anyway, but I don't do that kind of work. So anyway, sorry, is that a question?
Yeah, well, first of all, that actually is a really cool anecdote. But I was going to ask you, so are you saying that L in this case represents the diameter of the pipe in this equation? If you had
Okay, so for in a pipe, so let me go ahead and make that clear. So Reynolds number in a pipe, we would do, I usually would write it as U, or I guess we could say U bar times the diameter over the viscosity for in a pipe. Okay, and if you wanted to write PIPE, that would be fine. For us, I don't think we're going to calculate Reynolds number outside of pipes, but basically, if you work in some other kind of, if you're like, okay, I'm working in I don't know, just some sort of other thing. I'm working in a river. Well, how do you get the Reynolds number in a river? Well, there is a defined way to do that. How do I, I've got a a particle, and it's, I'm doing wastewater treatment, and there's a particle of poop or just waste or whatever, and it's sinking. Well, there's a way to calculate what we call a particle Reynolds number that's associated with that particle. If you're, so it depends on what kind of system you're in. There are all kinds of empirical methods for everything. And so basically what you would do is you would say, I want to know the transition for this particle settling through water. And you would look up what the empirical way to do that is. And if there's no empirical way, then you would do it your own way. You would say, okay, I want a Reynolds number. I need a U, an L, and a viscosity. Well, the viscosity of the fluid straightforward. For this velocity, you might use the fall velocity of the particle, the terminal fall velocity of the particle. And for this length scale, you might use the length scale of the particle. And you just have to figure that out, But usually if something's already been done, you're just going to look up how they've done it in the past. So in the case of the pipe, diameter of the pipe, mean velocity of the flow. Okay.
What is that fancy V on the bottom called again?
That is called a nu. So the way we would say that is we would say NU. And so remember, mu equals rho times nu. This one is easier to work with. This one's much easier to work with. Easier to work with. Easier. So this equation is easier to work with. And really it's because this viscosity is easier to work with. It has units of either feet squared per second or meters squared per second. And those can be really nice to work with. And so typically that's what we'll use. For water, I think it's 10 to the minus 6, I think, meters squared per second, and 10 to the minus 5th feet squared per second, I think. Can't remember exactly, but it's some nice clean number, which is easy to work with. Anyway, so we're going to do this so many times by the end of the semester that this will be easy for you. Yeah. So any other questions on that before I move on? Okay. So clear all drawings. Okay. So the next thing we're going to talk about is dimensionality. Gonna run out of time here. Dimensionality. Okay. And this is just about how you can simplify your problem. And this is basically, I'm just going to use an example. So 1D example would be flow in a pipe. Okay, so basically, like if you have a problem, and unless the problem is asking you something very specific about, say, the difference between the wall and the center, which usually it is not, then basically we're just worried about the flow in this direction. Okay, and so in this case, we usually will neglect differences in velocity, pressure, etc., transverse to the flow. Okay, so we're basically just going to act like it's just going in this direction. Okay, unless they're asking something specific about, the velocity profile, we're going to basically pretend like it doesn't have one. Okay. 2D, this is my favorite because this is like a lot of my work. So my example here is flow through a shallow marsh. Okay, and if you guys come to my office, which I'm here right now, but I'm not usually, you'll see pictures of like a river delta, and basically the flow comes out and it goes and the water spreads. Okay, and it's actually dropping sediment as it goes. Okay, this is all land on the sides here. It almost looks like a tree of some sorts. Okay, they actually use some dendritic models to describe some of this stuff. Okay, but you can imagine the flow going like this. Okay, and if you got a case like this, and this, say like in my case, this thing is a 1/4 mile wide, but its depth is like a meter. So in that case, we're going to worry about how it varies in this direction. and how things vary in this direction or the radial direction. Okay, but I'm not going to worry about the up or down. Okay, the vertical in that water column. Okay, so in this case, we can neglect differences in the third dimension, in whatever that third dimension is. So in my case, that would be vertical, but you might do it some other way. Okay, and so for these cases, you might use Cartesian, x, y. Cartesian, so you might use x, y coordinates, or you might use polar, okay, r theta. Okay, I don't think we're gonna have to use r theta in this class, although there are a lot of, like, this very well lends itself to r theta. But, you know, yeah, you know, I don't know. There are a lot of examples that work that way. Okay, and then the last particular case, so three-dimensional, the example that I like to think of here is wind in the mountains. Wind in the mountains. Okay, I had a professor at Berkeley who, she did a lot of work on this kind of stuff. See, and I think you can kind of imagine that, you know, you've got some mountains here, you've got a mountain range, and it's doing whatever it is that mountains do. And you can imagine that this flow as being affected, you know, by this mountain range, and it's being pushed upwards, downwards, in all different directions. And so you can't really neglect anything. Okay, so in this case, the flow varies in all three dimensions. Okay, so you can't neglect anything. Okay. And so it's something that, you know, you may want to consider. And of course, there's a lot of times, you know, like if you're like me and you read a lot of papers, you know, scientific papers, and you get stuck on something, you just stare at it and you go, you know what? The problem sometimes is they assumed that a system could be simplified by going to 2D, and it really can't be. And sometimes, you know, the problem is that I just can't understand what they did. So, you know, you get all excited because you're like, they're wrong, they're wrong, they're wrong. And you go, oh, I'm wrong. Okay. One of the things you always got to remember, awful lot of smart people in this world. A lot of dumb people too, but I like to think that even those dumb people, you know, are smarter than me in some ways. You know, and I like to believe that I'm smarter than them in some ways. So, anyway, so this is dimensionality. Any questions on this?
No, sir.
Okay, I'm going to clear all drawings, and I'm going to move on to something a little bit more engineering. Okay, so we're going to do the volumetric flow rate. I really miss being able to do this on my PowerPoint. I wonder if there was a way that I could do that. I bet there is. Okay, so this is so earlier I kind of gave you this U bar idea, or U bar or V bar, which is kind of like the average velocity. Okay, and this is kind of how we're gonna drive at that a little bit. And so what I want you to imagine is, I want you to imagine we've got a pipe. Doesn't have to be a pipe, could be a river, right? You know, if anybody pays any attention, if you pay attention to the river, you might look out there one day, and if you go to usgs.gov, water data, whatever, I forget what this, I think it's waterdata.usgs.gov. You can go see how much water is flowing down the Mississippi River on any given day. I haven't looked in a while, but let's suppose it's, you know, 225,000 CFS. So you might say, oh, or 400,000 CFS. So let's suppose that's the flow rate. For some reason they use Q in the Mississippi River. You don't have to write this down. I'm making this up. Okay, let's just imagine. Okay, what does that mean? That means if I were to go out there and here's the river and it's like going like this, and then, you know, so here's the city, right? And so here's Audubon Park. And then they've got a little, they're figuring out that at Audubon Park, that 400,000 cubic feet pass that point every second. So that means if they wait 1 second, that this volume right here, that's all the flow that passed that, you know, this line, and that's 400,000 cubic feet, and that much passed it in 1 second. Okay, and so that's kind of the idea. Okay, now obviously the Mississippi River is a large river, certainly in the U.S. standard. Of course, it's the biggest. Compared to the Amazon, it is just a drop in the bucket. It could enter the Amazon and the Amazon probably wouldn't even feel it. The Amazon is amazing. I would love to go see it. Okay, but what I want to drive home here is this is cubic feet per second, so it is some kind of volume. Okay, so this is volume passing a point. Let me just do Q in general. Okay, so Q equals volume passing a point in a given amount of time. Okay, it has units of volume over time. So usually that's length cubed over time. You might see it in gallons sometimes. Gallons is a really unfortunate unit, like everything in the British system, which should just be called the American system. Although apparently in Brexit, they're now going to they're starting to go backwards and they're starting to go back to the imperial units. Isn't that lovely?
Yeah,
What idiots.
They're starting to use like American.
Well, they're really British units, but we've adopted them really. And I thought we were the only country that used them. But if you go to England, they use a real strange hodgepodge of units anyway. They will use miles. And like if you can get on a scale in England, they use weird things like stone, and you're like, I don't know what, it's just so weird. But anyway, the fact that they would go backwards is just so crazy to me.
So yeah.
So anyway, like obviously I understand why it's difficult for us to switch. Switching is difficult. Anyway, it doesn't matter. So anyway, so if you have gallons, just know that there are 7.48 gallons in a cubic foot. Okay, or you'll just have to look that up, right? So if I ever give it to you on a homework or something, I think this is right. You just have to look it up. Okay. Maybe I'll give you one with gallons just to make sure that you know how to do it. Okay, so anyway, so there's this last little bit here, and I hate this bit. So what I want to make a point of here is that the way that we calculate Q is it's two different ways. And I'm staring at these trying to remember oh yeah, okay. So we can integrate over the area, V times the area. Okay, so okay. And the other way we can do it is we can say Q equals okay, so these are both annoying. Okay, I'm not going to lie, these are annoying. Okay, but what this dot product, for those of you guys who have not thought about dot products, for a while, what it basically says is it says like, okay, so if I want the volumetric flow rate into this pipe, okay, so if I want the volumetric flow rate coming into this pipe, okay, and the flow is coming in, if the flow, let's imagine it's not going straight in like that. Let's suppose it's all, chaotic and whatnot, or let's imagine here's the surface that I want it to cross into. But let's suppose for some reason it's coming in at an angle. Okay. So the thing that you have to remember if it's coming in at an angle is that the stuff that's going this way is not entering or exiting. It's not doing anything. Right? It's actually only the stuff that is going perpendicular to that surface that's coming in. Okay. So basically, if it's at an angle, well, hopefully you can already see what it is that you need. Well, you need the X component of this, right? So we need this component. So we need that velocity, okay, times the area over where it's going in. So let's imagine we got a little dA here, dA. But that's really the X component of that velocity. So it's going to be V cosine of theta, right? And we would integrate that over the whole area, right? Now, does this come up very often? No, it really doesn't come up all that often. Okay, that's the dot product. Okay, and so this is where the dot product comes from. So if ever you guys are wondering, if you're like, oh, the dot product, can't remember how it works, but I know that if I've got like A dot B, it equals A B cosine of the angle. Well, that's where that cosine comes from. Okay. If ever you guys were wondering, well, what is all this silliness? Where does that cosine come from? That's where the cosine comes from. Okay, hopefully that clears that up for you, because I could never remember what that was. Anyway, but the cleaner way that we typically do with this, instead of doing this, we don't do this very often. What we do instead usually is we look for the V average. Okay, so I'm going to call it V bar. And, you know, and you might make a note that that's the average, equals the Q divided by the area. Okay, or Q equals V bar times the area. Because the way to think about that is I've got this thing right here, and let's suppose I've got a velocity profile, whatever it looks like. Okay, it looks like I've kind of drawn a fairly uniform one, so this is probably turbulent. Okay, but what I'm going to do is I'm going to say, you know what? I'm going to take this average velocity, which might be like right here, and I'm going to apply it over the entire cross section. Okay, cross-sectional area, and that's going to be the total flow rate. Okay, and hopefully that's logical enough for you. Okay, so let's do mass flow rate. Let's go here. Let's do mass flow rate. So mass flow rate. Okay, very similar, but instead of getting like, you know, a volume per time, we're going to get a mass per time. So what's nice about this is to go from volume to mass. Anybody want to tell me how we go from volume to mass in fluids?
Use the
Density, volume to mass, perfect. Okay, so basically m dot, okay, that's the mass flow rate. Okay, we've got the volume per time, and we're going to multiply that times Q, rho. Okay, so this is volume per time, and we're going to multiply that by mass per volume. So we'll get mass per time. Okay, so this becomes rho average velocity times the area. Or if you want it in the integral form, we would do over the area of rho v dot dA. Okay. And it is measured in units of mass per time. So usually it's kilograms per second or slugs per second. Okay, one thing, and this is very key, so I'm going to go ahead and box it even before I write it. Okay, mass is conserved. Okay, volume is not. Okay, however, in this class, where we all usually dealing with incompressible flows, okay, volume will be conserved. Okay, and this is like really critical because usually we're going to do this, but not always. Okay, so just be aware. So what will happen in a lot of cases is if the fluid is incompressible, then the rho is the same everywhere, and algebraically it just ends up canceling out, and so then you end up with a volume is conserved. Okay, so I've got two examples we got to work. We have not a lot of time, so I'm going to roll with this, and let's see what we can do. Okay, so luckily, you know, these are quick to work. Come on, you know, clear all. Okay, so here's example one. This is going to be one of the important tools that so manometers and mass conservation are going to be like example one. I guess we're not doing continuity yet, but we're kind of along those lines. Okay, oil S equals 0.86 flows through a 30-inch pipe. Oh, at 8,000 gallons per minute. Oh, there it is, gallons. Okay, find A, Q and CFS. Okay, that's easy. B, average velocity. And C, mass flow rate. Okay, I'm gonna go ahead and do the first one because it's already given us Q. Okay, and so I'm just gonna convert it just so you'll know how to do this. 8,000 gallons per minute. Okay, so all we're gonna do is we're gonna say, well, Q equals, well, it's, 8,000 gallons per minute. So this is just a conversion. My assumption is that most of you guys don't need this. 7.48 gallons per cubic foot. Okay, and then we'll go 1 minute, 60 seconds. Okay, and so we'll just multiply all that out. I didn't give myself 5 sig figs when I did this, so we're just gonna have to leave it as 17.8 CFS. Okay. So now for part B, I want to know the average velocity. So what we'll do is we're going to go, okay, well, the average velocity, oh, this is A. Here's B, the average velocity. Well, let's start from the original equation. Q equals V bar A. Okay, so let's see here. Q is 17.8 CFS. Okay, the V bar is what we're looking for. And the area of a pipe, usually you do pi r squared, but in this class, it's going to get a lot easier if you do pi d squared on 4. So we're going to plug in the d, which is 30 inches. So we're going to plug in 30 over 12 feet squared. Okay, so we're just converting to inches, to feet. Okay. So we're going to end up with V bar equals 3.63 feet per second. Okay. Or 3.63 feet per second, depending on how you want to write it. All right, and then the last bit here is the M dot. Okay, so we want M dots, we want a mass flow rate. So to get a mass flow rate, we're going to do the density times the flow rate. I'm sorry, I know I'm doing this one quickly. Please holler if something doesn't make any sense. Okay, so let's see here. The density of this, well, we've got an S up here. So you can say 0.86 times the density of water, which is 1.94 slugs per cubic foot. Okay, so that's the density of the oil. And then the Q is right here. So 17.8 CFS. Okay. So we want to check our units here. This foot cubed and that foot cubed are going to cancel and be left with slugs per second. Okay, so the M dot equals some number of slugs per second. The number is not important. 29.7 slugs per second. Any questions on that?
No.
Okay, I will clear this. And then I'm going to do one more. This one's a little bit harder. Example 2. Okay, let's see here. We got air here. Okay, air. Get a density given 1.4 kilograms per cubic meter. Cubic meter travels in a 1 meter square duct, DUCT, with a vertically linear velocity profile. Maxing out 10 meters per second in the center of the duct. In center of duct. Okay, find. Looks like we're going to do the same questions. Okay, find Q in CFS. 2, V and 3 M dot. I guess whoever wrote this question only cared about Q being in CFS. I guess they figured once they got you there, you'd be good to go. Okay, looks like I'm going to run over a little bit. I apologize. If you need to leave, do so. So this is a duct, 1 meter by 1 meter. And this is kind of interesting because what's happening is, if I do the velocity profile from this, here's my 1 meter. Here's my velocity profile. So I'm just going to kind of plot it going through that duct. And so we've got this flow doing this. Okay, and it's going 10 meters per second in the middle. Okay, that's going to be at like a y of what, a half a meter, right? Okay, and this is my velocity. So this is, I guess this axis here would be u as a function of y. Or this would be u as a function of y. And this would just be u. This would be y. Okay, so all of that's going into or out of this duct right here. Okay. And so in order to solve this, like this stinks because it's non-uniform. Okay, it's non-uniform in the cross section. So we're gonna have to integrate. Okay, so the formula is Q equals the integral over the area of VdA. Okay, well that's annoying, right? So here's how I suggest we do this. So first I need to know a formula for U, right? So I'm going to do U. I know this is a line, so I'm going to do y equals mx plus b. But in this case, I guess it's U equals my plus b, right? And so what I'm going to do is I know I've got a point here where the velocity is 10 meters per second. Okay, I'm looking for this m. And that 10 meters per second, well, I have 2 points basically. Actually, let's do the first point. Let's start with the first point, which is right here. Okay, right here. Okay. And so I'll say, okay, well, if u equals 0 and x equals 0, then b is equals to 0. Okay, that's easy. So b goes away. Okay, then I'll do the second one. Okay, so u equals my. So u equals my. Okay, and so u is going to be 10 meters per second at this point right here. And then m is, well, that's what we're looking for. And the y at that point is a half a meter. Okay, so m then equals 20 per second times y. Okay, so I can say that u in the vertical for the bottom half equals 20 per second times y. Oh yeah, what? This y doesn't belong here. Okay. Okay, and that's only for the bottom half. And what I'm going to do is I'm going to assume the top half and the bottom half are the same. Okay, so what I'm going to do here is I'm going to say Q equals the integral. I'm going to do this twice because I'm doing the top and the bottom. I'm only doing the bottom half, and then I'll multiply times 2 to get the top half of 20 per second times y times dA. Okay, so now what I'm going to do is I'm going to think about that dA that it's acting on, and I'm going to note that, you know what, it's not doing anything particularly interesting across this cross section. So I'm going to make my dA b times dy. Okay, so I'm going to erase this, make this b times dy. B, of course, is 1 meter, but I'm just going to leave it as b for now. It's a constant 1 meter, and I'm going to pull that right out. Okay, so there'll be a b right here. I'm going to erase this b, and now I'm just going to go right ahead and integrate this thing. Okay, and this should become, let's see here, 20 per second, 2b. Those are all constants. and I'm gonna get y squared on 2. Okay, and I'm gonna integrate that in the y direction from 0 to 1 meter. From 0 to 1 meter, and that's gonna be my flow rate. Okay, noting that B here is 1 meter also. Okay, so if I plug all that in, what do I end up getting? I end up getting a half. Those cancels. For some reason, oh, right, sorry. This doesn't go all the way up to 1 meter. It only goes up to a half a meter because I'm only doing the bottom half. Because the top half is taken care of by multiplying that times 2. So if I do all of that, then the Q is 5 cubic meters per second. Okay, and then this last bit is real quick. Sorry, I'm about 5 minutes over. And then to get the V dot and the M dot, those things are fairly straightforward once you've done that. So I'll just go ahead and do that. This bit was a little bit involved, but then I'll get the B by doing V bar equals Q on A. Okay, so that's 5 cubic meters per second divided by 1 meter by 1 meter. So that's 1 meter squared. So V bar equals 5 meters per second. So that's easy, or easy math anyway. And then for part C, M dot equals rho times Q. And so M dot equals 1.4 kilograms per cubic meter. Okay, times Q, which is 5 cubic meters per second. Okay, so the M dot's going to equal 7 on the nose. And that's kilograms per second. Okay, sorry for the quick presentation there. I was running over. Sorry to run over. I tend to do that a lot when teaching online. And I never have that problem in person. Any questions on that?
Yeah, the shape of this was going to be that V shape because it said vertically linear, meaning that it's a linear curve with respect to the vertical axis. Just
yeah. Although I guess linear curve is kind of an oxymoron, but yes, right. Linear means line, so yeah.
Sure.
Yeah, but yeah, exactly. So because it says linear, because it says a linear profile maxing at 10, I guess like really in this case, I would probably if I gave this to you on a test or something, I would probably draw this velocity profile for you. Yeah, probably because this one's it's a little bit weird that language is a little bit confusing. I think there's a, go ahead.
That's sort of like kind of a side view, right? When you have that velocity profile, it'd be like if we were looking at the duck from the front in the left image, and then you kind of look at it, you kind of rotate it and look at
that would be a good way to think of it. Yeah, we can think of it like, I guess if I were a better drawer, like this, with it kind of like doing this. Yeah. Okay. That would be right. Yeah, something like that. if I could draw that. Any other questions?
I have a question about the test, but I can wait.
Okay. All right, well, I'll open it up to test questions. Then if no one has any other questions about this.
Okay, I was gonna ask what exactly, like in terms of what chapters or maybe what lectures or both.
Okay, hold on. Let me.
Is this today what we learned are gonna be on the test? Or?
No. I never do that. So the rules for my test always, I mean, this won't really help because you'll forget by the next test. Hopefully, because hopefully you have more things going on in your life than trying to remember this. But I always want you to have had a chance to turn in your homework and ask questions on it. So basically, I'm staring at the schedule right now on my phone, and it's let's see, so it's intro through forces on curved surfaces. So if you look at the your real-time schedule, it's basically the first 4 rows. And if you want to know what chapters in the book, there's like reading associated with those chapters or that material.
Right.
So it's basically chapters 2 and 3. Well, I guess that's not true. I look at your textbook from time to time, but I don't pay attention to what chapter I'm in. So, so it looks like I'm in chapters 2 and 3.
Okay, thank you.
All right, you're welcome. Anybody else? I had an iPhone leave. I always like it when it tells me that an iPhone left. Let's see what we got. We got 6 things. Are these in the chat? Is the test in person? Yes, the test is in person. Mine's still frozen. Mine froze again. Doc, you need an ad blocker. Highly recommend that YouTube guy. I don't know who that YouTube guy is. 3.
I think.
Huh?
I think you should talk
What's
about
that?
Smarter Every Day.
About what?
Smarter Every Day, the guy on YouTube.
Oh yeah. I get excited about enthusiastic teachers. So yeah, that guy's good. There's another guy who does the glitter bombs who's pretty funny. Mark Rober, maybe. Yeah, I don't know. Those 2 guys apparently are buddies, which makes sense.
I had a question.
Sure.
What's your idea of I guess a one-step problem? Because I mean, with your previous tests, I guess in statics, I've never seen a simple problem, I guess.
Yeah, I don't know. So like, I don't know if you look in the fluid properties, there's some things like, or how about like, I think I asked a question, so like think back to some of the homework I've given you guys where it's like, where I'll say like, oh, does this fluid cavitate? I think there were some questions on like the bulk modulus of elasticity, where it's like, it's just like one equation, you just solve it, and you move on with your life. Something like that. And I'm thinking back to the fluid properties really, because those are the only things that I can think of that would be simple enough for a one equation problem. Let me see what we got here. I could give you a capillarity problem where I gave you the equation for the capillary rise. Usually in my old tests, I make people solve for the equation to capillary rise because I give it to them like in a way that the given equation is not really going to work. I don't know. It's just going to be an easy problem because usually like if you're doing a force on a gate, you have to figure out, H sub C, Y sub C, the moment of inertia. You got to figure out all kinds of stuff before you can solve it. And then you need to solve like 2 or 3 equations, 4 equations before then you got to sum moments or something. And so that's pretty involved, but I might do something, just simpler, a one-step problem. I don't know. So just go back, look through your old homeworks and, I might just pull something out of there. I don't know.
Between our Connect homeworks and the old test that you posted, we should have enough to like prepare for this test.
Yeah, absolutely. And if you're sitting there and you're like, you know what, I really struggle with a certain concept, what I recommend is either, really what I recommend is going to the old homeworks, as well. And I recommend, for the true false, because I have a lot of students that just do really badly on the true false. And what I recommend is just read your notes. So let's suppose you study for the next 2 nights. What I would do is I would begin each night, read all your notes. There's probably not that many words in your notes, just read them. Read it at the beginning of your study session, read them at the end of the study session, and then do that again tomorrow night. And really what you're looking for is a concept where you go, that doesn't make a lot of sense to me. And what you want to do is you want to have that concept sink in so that you're ready to, so that if I ask you a question about it, it's sunk in. Because, a lot of times what happens is people try to like kind of memorize or something. And then I ask a question about it and it's like, oh, wait, it turns out I didn't really understand that. So, it's just, I don't know. That's the idea, I guess. I would read your notes for the true false.
Okay, and when it comes to formula sheets and stuff, are we allowed one?
No, I'm going to give you the FE formula sheet, which you can find in resources under Moodle.
Okay, thanks.
That one is, so I would study with that thing out so you would know how it presents the data. What I want is I want you to, if you miss anything, I want you to miss it in this class and not on the FE. So my hope is that, you know, you'll look through this thing and you'll learn the limitations, you know, the strengths and the limitations of this sheet, right? Because there's some places where I'm like, oh, it does this, and that doesn't make a whole lot of sense to me. But you won't know that until you look at it. So I need y'all to look at it. It's kind of my hope. You know, the goal really is for you guys to have that printed out and use it on your homework. So you miss points on your homework, and then so you won't miss it on your tests, so you won't miss it on the FE. But you know, I get ignored when I tell people to do that. So, but that's my recommendation. Any other questions?
Yeah. What floor is the auditorium on?
It's on the first floor. It's EN 101, and you don't actually enter the building in order to. Hold on, I'm getting another call. Oh, it's on the first floor of the engineering building, but you don't actually enter the rest of the building to go into the auditorium. It's like across the breezeway. So it's like across from the snack rooms, I guess, or across from the entrance by the elevators.
Okay.
Yeah, just show up. I mean, if you just show up early, hopefully I'll be out front. What's up?
Nothing. I'll try.
Okay, it's yeah, it's a big auditorium. It's the opposite thing. It's called the DOHSE, the Doze Auditorium. And if you walk around, people will know where it is. Yeah, so it's very big. There should be plenty of space for us to spread out.
Awesome.
Any other questions? All right, well then I will be signing off. I will see you guys in 2 days. If you need me, office hours at 3:30 to 5:30. Have a good one.
Thank you.
All right, see you
Thursday.
guys.
Thanks.